All right, so today we are going to cover Chapter 9. Okay, and this is on, so we are doing inference for numeric variables. This is kind of a little bit of a lag here. I don't know what's going on. Okay. What is this? I have no idea what I'm doing. Okay. Inference for numeric variables. Okay, so as opposed to Chapter 8 where we were dealing with categorical variables, this time we are dealing with sample means. Okay, so versus Chapter 8, which was categorical variables. And we dealt with sample proportions. Okay, so maybe we'll begin with just a few symbols for Chapter 9. We have sample statistics. Okay, and so for as far as sample statistics go, we have the sample mean. And what symbol do we use there? Well, I just wrote it, X bar. And the sample standard deviation, which is what? S. Okay, good job. And then we have the population parameters. Okay, and for that we have the population mean, mean mu. And we have the population standard deviation sigma. Okay, so we have mu and sigma. Okay. And so we can talk about the sampling distribution the sampling distribution of X bar, okay? And so in Chapter 8, we talked about the sampling distribution of P hat, which was the sample proportion. In Chapter 9, we are dealing with the sampling distribution of X bar, our sample mean, okay? The central limit theorem told us that the sampling distribution of X bar, of P hat, could be approximated with the normal distribution. Same thing here, okay? We have the central limit theorem. Also applies to the sampling distribution of X bar. Okay, what did the central limit theorem say regarding P hat? It said that we can approximate the sampling distribution of p hat with the normal distribution, right? Okay, same thing here. Central limit theorem says this thing can be approximated with a normal distribution. Okay, so let's just kind of discuss a little bit about the sampling distribution of x bar. Okay. So so this past week you got a lab, right, on pennies or something. Okay, and I don't know if you guys already finished. Some of you probably have. Okay, and if we look at the population of penny ages, it looks, I don't know, it looks something like this, right? I don't know, it's a bit skewed or something, I don't know, if I recall the data correctly. Okay, and so this is the population distribution, okay? The distribution of the population. Okay. What is a sampling distribution again? So the idea is you have this large entity, the population, okay? And from this population, you take a little piece out. You take a random sample. So this is sample 1. And from sample 1, you record an x bar. Okay? And then you take another sample out of the population. This will be sample 2. And from there, you record another x bar, okay? And then you do this over and over and over again, okay? So you take random samples out of the population, and every time you get another x bar and another x bar and another x bar, okay? So you get samples, okay? Okay, and then we're going to keep track. We keep track of all of the x bars we see. Okay, and the result will be our sampling distribution. Okay, and that's kind of the point of what you guys are doing in the lab is you have a numeric variable, this time the age of pennies, and then you're going to just repeatedly sample from that population and record x bar, okay, which I think Fathom calls a measure or something like that. You just repeatedly record all of these different x bars, and then you keep track of them, okay? And then so the thing that you end up getting at the end is you end up getting something that looks like the normal distribution. Okay, so this is the sampling distribution of x bar. Okay, and we say, this looks like the normal distribution. So we can say this can be approximated with the normal distribution. Okay, and according to the central limit theorem, is that if the population has some mean mu, okay, the mean of our sampling distribution will also be that same value mu. Okay, so the mean of the sampling distribution is equal to mu, which is our population mean, and the standard deviation of the sampling distribution is equal to sigma over the square root of n. Okay, and so, so let me just talk about the standard deviation or the spread of our sampling distribution. Okay. Okay, is kind of defined by the standard deviation, okay? Is the standard deviation, which is equal to sigma over the square root of n, okay? And so we see that it depends on the sample size. Okay, and because n is in the denominator, so larger values of n correspond to smaller corresponds with a smaller spread, okay? And if we think about it, that makes sense, right? So if we're taking, let's say we take a random sample of people, and we're going to look at the average IQ of this random sample of people, okay? If I'm only taking a random sample of, let's say, 3 people, okay? Now this won't happen all the time, but it's going to be quite possible for the average IQ of those 3 people to be quite high. You could get 3, just by random chance, you could get 3 very smart people with high IQs, and therefore the average of those 3 people will be quite high, okay? On the other hand, it's very possible to get 3 people with low, and all 3 of them have low IQs, and the average is low, okay? On the other hand, if you took a random sample of 100 people, okay? With 100 people, it's very unlikely for all 100 people to have high IQs, and the average of that 100 of those 100 people to be very high, okay? So, it's also very unlikely for the average of those 100 people to also be very low, okay? Just because with 100 people, you're going to get some people with high IQs, some people with low IQs. They're all going to kind of cancel each other out and balance out, and the average of those 100 people should be very close to the population average. Okay? And so if we look at the amount of spread that exists in X bar, there's going to be more spread for smaller samples, and larger samples will have less spread. Okay? So larger values of n corresponds with smaller spread, and then small samples will have will exhibit larger spread in X bar. Okay. Okay, so we can say, the sampling distribution of X bar, in summary, we'll say the sampling distribution of X bar is approximately normal, not with a mean of mu, with a mean of sigma, with a mean of mu, and a standard deviation of sigma over the square root of n. Okay. So far, so good? I'm hoping. Okay. All right, so let's try out a problem here. We'll make a clicker problem and make sure we got this down. Okay. Okay, so all right, so we will say. So I just looked this up. Where did it go? Average weight of a dairy cow. Okay. I was just curious. All right. So I don't know. Okay, we can now. I would just decided to go with Jersey cattle, but I don't really know. Apparently, there's all sorts of different dairy cows. I don't know too much about these, but okay. All right, so we will say the average weight of a dairy cow, and so this is, we're talking about the population, right? So the average weight of dairy cow is, we'll say 1,500 pounds. Okay, and we'll say the standard deviation is 150 pounds. Okay. Okay, and then so now I'm going to ask a question here. I'm going to say you take a random sample of 9 dairy cows. Okay. I'm going to ask, what is the probability that the average weight of those 9 cows is over 1,600 pounds. Okay. So let me find some answer choices here. So we're asking, what's the probability that the average weight of those 9 cows is over 1,600? Okay. Okay, so I got, this is one possibility. Okay, so go ahead and try that out. Okay, we'll say maybe another 30 seconds here or something. So again, here we're looking at the sampling distribution, so keep that in mind. Okay, I'm gonna hit stop here, so if you haven't clicked your buttons, click your buttons, okay? All right, here we go. Stop. Okay, let's talk about this. So here we are asking, what is the probability that the average weight of those 9 cows? So we're looking at what is the probability, basically, that X bar is over 1600. Okay, this is what we want to know. Okay, so we have X bar from what we wrote on the previous page. The X bar is going to come from a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n. Okay, and so if we look through the problem, it says in the population the mean weight is 1500. So this is going to be our mu, and then the standard deviation in our population is 150. That's our sigma. Okay, and then here we are taking a random sample of 9 cows. So the number 9 is n. Okay, so here we've got X bar coming from a normal model with a mean of 1500 and standard deviation 150 over the square root of 9. Okay, 150 divided by the square root of 9 is going to be 50. Okay, so if we create our picture here, our mean we're going to end up, if we put 1500 in the middle and we put 1600 out here, our z-score for 1600 is going to be 1600 minus 1500 divided by 50. We get a z-score of 2. Okay, and we want to know what's the area out here. Well, this side is 0.9772, so this is going to be 0.0228. Okay, so our answer is B. All right, let's see how you guys did. Okay, so a good number of you guys got that correct. And then as far as the other ones go, so you would get the answer for A if you just did 1600 minus 1500 divided by 150. Okay, if you divide it by 150, that is not taking into account that we are looking at the average weight of 9 cows. That would be, what's the probability that one randomly selected cow is over 1600 pounds? Okay, so the probability that one randomly selected cow weighs over 1600 pounds, that happens about a quarter of the time, okay, 25% of the time. But then if you take 9 cows at random, the probability that the average of all 9 cows ends up being over 1600, that only happens about 2% of the time, okay? And that's, we are observing the effect of dealing with a sampling distribution rather than the actual parent population. Okay, so here this is an application of the central limit theorem. Whenever we apply the central limit theorem, we should check the conditions to make sure we can use the central limit theorem. And so the conditions are the same as before. It's just the way we check them is just a little bit different for the second condition. Okay, so we should check conditions. I'll say checking conditions to use the central limit theorem. Did you guys see the? Oh, I don't. Never mind. Okay. All right. What are the conditions for using the central limit theorem? Number one, our samples should be. Yeah, sample is random, and individuals in the sample are independent, right? Okay, and so this condition is exactly the same as before. So we have the random and independent condition. Okay, so that's the same as before. We also have the large sample condition, that our sample must be large enough. Okay, so in chapter 8, the way we checked this was we said you have to have at least 10 successes and at least 10 failures. And so we said, n times p has to be bigger than 10, and n times 1 minus p has to be bigger than 10. So it's different here because we don't have a p, we don't have a proportion to deal with. Okay, so here it's a little strange. We just basically n needs to be quote unquote large enough. All right, and so that's not very helpful. Okay, so what does it mean to be large enough? N needs to be large enough. Okay, so if the population is normal, then any n is large enough. Okay, so if the population is normal, okay, or at least unimodal and symmetric, then almost any n is fine. Okay, then almost any n is large enough. Okay, so if the population is normal, really you can have n as small as 1 or 2. Okay, if it's just unimodal and symmetric, but not perfectly normal, then maybe you need samples of size 5 or something like that. Okay. On the other hand, if the population is not normal, meaning it's like skewed or something, okay, so if the population not normal, so skewed or something, okay, then you need a larger n. Rule of thumb. Do you know the origin for the phrase rule of thumb? It's kind of terrible. It's like you were legally allowed, if you were a man, you were legally allowed to like beat your wife with a stick as long as the stick wasn't bigger than your thumb, which I don't know. Huh? It was a different time back then, and yeah. But anyway, but rule of thumb has stuck around. I don't know if we have a better phrase for an approximation here. Okay, rule of thumb is that n is greater than or equal to 25, generally big enough. Okay. And but in very skewed situations, okay, but in very skewed situations or in very skewed data, even larger n is needed. Okay. Some textbooks will say n greater than or equal to 30 is big enough. And it's just like, usually that's big enough for most circumstances, okay? And this is to apply the central limit theorem, okay? And what's kind of the big picture point of the central limit theorem? Okay, so in the big picture point of the central limit theorem is that the sampling distribution of whatever, of p hat or x bar or whatever these things we're looking at, the sampling distribution can be approximated with the normal distribution, okay? Because all of this stuff depends on kind of this normal distribution approximation or this kind of inference there. And so the central limit theorem says the sampling distribution can be approximated with the normal. So basically, if these conditions aren't met, you know, a sampling distribution still exists. It's just not going to follow the normal distribution. Okay. All right. So the large sample condition, and then lastly, we have what? Big population condition. Okay. And the big population, that's the same as before. The population needs to be at least 10 times bigger than our sample. Okay. Okay. Yeah, that rule of thumb, that's kind of terrible. I mean, not kind of, it truly is. Okay. We need a better phrase. All right. All right. Big population condition, large sample condition, and something exciting is happening. All right. Okay. So if you recall, when we were dealing with p hat, we said because we know that the sampling distribution follows the normal distribution, when we observe a p hat, we can say that the population proportion p is close by, right? We're kind of remember this when we're dealing with confidence intervals? Okay, so I'll say recall a confidence interval for p hat, not for p hat, for p based on a sample with p hat. Okay, now what went into the middle of our confidence interval for p? It was our best guess for p based on the data. And what is that value? P hat, right? Okay. And then we said plus or minus the margin of error. Okay, how did we make the margin of error? Z star, a critical value. And the critical values were based on the basically normal distribution because of the central limit there, right? Okay, so we have a critical value, and we multiplied that by what? The standard error, which was our standard deviation of the sampling distribution. And that was the square root of p hat times 1 minus p hat over n. And why did we use p hat? Why didn't we use p? Because p is unavailable when we're making a confidence interval, right? Because we do not know p. Okay. I'm hoping this is familiar, looking familiar. I hope. Today I'm a little worried. Okay, and then, okay, so we're going to basically, using the same idea here, okay, we'll say a confidence interval. This time we are going to make a confidence interval for the population mean mu. Okay, based on a sample. Okay, so in the center, or in the middle, I will put my best guess of mu, best guess for mu based on the data. And what's that going to be? So based on the data I have, what's my current best guess of the population mean? Yeah, the mean of our sample, x bar, exactly, okay? And then we will go plus or minus the margin of error, and how do you think we're going to make the margin of error? Okay, we'll have a critical value based on the normal distribution. Okay, it's going to change, so I'm going to just I'm going to put in a z, and I'm going to just kind of put a parentheses here. Okay, and then we're going to multiply that by our standard error. Okay, what's the standard error of the sampling distribution of x bar? What is that? Sigma over the square root of n. Okay, do we see a problem here? Is there a problem? Maybe there's no problem. I see a problem. Okay, the problem is this thing, okay? We don't know what sigma is, right? Here, with the confidence interval, we're basically saying, based on what I see in my sample, what can I say about the population, because the population is unknown, right? And so here, I'm looking at my sample, and I'm trying to infer about the population mean, okay? So do you think I'm going to know the population standard deviation? No, okay? I can't, I mean, there might be a weird situation, but there's almost rarely any times when you know when you don't know the population mean, but you happen to know the population standard deviation, okay? So the problem here is we do not know sigma. Okay? So what can we do? Instead of using if we don't know the population standard deviation, can we try to guess what that is? Yeah, okay. What do you think a good guess of the population standard deviation would be? The sample standard deviation, right? So if we don't know what population standard deviation is, okay, so we will plug in our best guess for sigma, which is our sample standard deviation S. Okay? All right. What ends up happening, though, is when you do that, x bar, we have to compensate, okay? So plugging in S instead of sigma, that's fine, okay? But what ends up happening is we can no longer just use values from the normal distribution. We have to compensate for it, and so I'm going to put in T star. This is a critical value, okay? And the T star is based on the normal distribution, but there's a compensation factor, okay? So the critical value is now T star. Is T star, which basically compensates I'm going to just write that, compensates for using S instead of sigma, okay? So, you know, when we were doing chapter 8, I said, hey, you can use p hat instead of p, and the math works out, and we're okay. In this case, when you use S instead of sigma, it messes things up a tiny bit, okay? And so you can no longer use 1.96 and 1.645. You can't use those z star values anymore. You have to adjust it a little bit, okay? And so there's like a little bit of a fudge factor that that gets mixed in here, and that will all show up in our t-distribution reference table. So on Wednesday, I'll pass out the t-distribution, and it'll have values to plug in here. Okay, so that'll be it for today. You can look for a practice quiz posted online in a little bit of time, and that will be that. Okay, we'll see you guys on Wednesday.